It's faster, right? But when we applied the diffusion effect, it generates in this manner. Overall, when you see a gap here, you divide this part accordingly. The traditional transformer-based LLM method generates tokens sequentially. It reads the previous part, then generates one word, puts it back in, and generates another word, and continues in this structure. Those who are familiar with diffusion models will understand this well. By modeling the diffusion phenomenon, which is similar to how a drop of ink spreads rapidly in water, this model also generates text in a similar manner. Just like text-to-image generation models, it produces the entire response all at once, and this can be iteratively improved. This makes it significantly more efficient compared to traditional LLMs. It is 10 times faster and 10 times more cost-effective, and it has actually been commercialized. This model, called Mercury, was developed by Inception Lab. As you can see here, it is the first commercial-scale language model. But how was it achieved? Using the diffusion paradigm. This model is known as the Diffusion Large Language Model, or dLLM, and it's ready for use right now. If you look below, you can immediately feel Inception's speed. While Claude and ChatGPT are still generating, Mercury finishes in no time. It only took 6 seconds, and it's done. When we look at our text-to-image generation models, the face gradually becomes more detailed and is generated in one go. So what does this mean? It means it can be done faster while using fewer GPUs. You see, instead of generating step by step, the diffusion model initially produces nonsensical outputs, but as it iterates, it gradually becomes more accurate. This makes the diffusion model faster. So let's take a closer look at this. This is the first commercial model in its early stage. Big tech companies have been diligently researching transformer models so far. By putting significant effort into refining this diffusion model, there is a promising potential to develop superior AI models with reduced GPU usage. Let's delve into this topic because InceptionLab.ai currently offers this technology for use. Although you might encounter an error message, it is remarkably fast. I personally tested it, and the performance is outstanding. Can you explain the operational mechanism of this model? Is there anything different? It's a bit faster, right? I added the diffuser effect and it generates like this. See how fast it is? It supports various prompts. Initially, it doesn't make sense, but it gradually becomes usable. It's very fast. I've explained the diffusion model many times. Let me briefly explain it again. This is for those who are new here. Look here. So, when we talk about training with this diffusion model, are we referring to training it on images? Consider this flower. When we have such data, it divides into two primary processes. The first is the forward diffusion process, where a clean state gradually becomes noisier. The second is the reverse denoising process, which starts with noise and progressively becomes clearer. In the forward process, it begins with a clean image or sentence and slowly accumulates noise. We deliberately add noise to the image, causing the flower picture to gradually become more distorted. This process is exactly what diffusion models aim to emulate. When training, the model learns to reverse this noise-adding process. Does that make sense to you? Originally, we intentionally added noise, but by training the model in the process of reversing the noisy state, it learns to gradually eliminate the noise bit by bit. This denoising process allows the model to restore a clear image, eventually generating an image in the form desired by the user. This entire sequence, where noise is incrementally removed to produce a clean image, is known as the diffusion process. Initially, it starts with complete noise, and as the iterations progress, you can see it gradually becoming clearer, right? In the same way that images are generated in text mode, instead of producing text in a linear fashion, it spreads out and creates content gradually. Initially, the text may not make sense, but the goal is to eventually form coherent and meaningful sentences. As you can observe, the performance is quite impressive. Here you can see Mercury Coder Mini and Mercury ... There is a small coder, a mini small model, which is the fastest in terms of processing speed, handling between 700 to 1100 tokens per second. When compared to smaller versions like Gemini Lite and Haiku Mini, this model can be up to 10 to 15 times faster, and sometimes even 20 times faster. However, the performance, when compared to this model, it is generally claimed to be similar or better. This is different from the improvements seen with traditional transformer models. The architecture is entirely different. Transformer models read the preceding text to generate the next part using the same format and rules they were trained with, but achieving this level of performance with a diffusion model is highly significant. Additionally, when visualized, the diffusion model's performance is clearly superior. This highlights the incredible speed at which it operates, iterating rapidly in one go, which simplifies hardware configuration significantly. Even when compared to smaller models, the fact that it can run so swiftly on smaller devices underscores its efficiency as an on-device AI. Additionally, with diffusion models, these features can now be implemented directly on smartphones, and API access is also being provided. Just like with Inception, we are currently conducting intensive research on diffusion models because we recognize the limitations of transformer models. Generating sequences step by step is extremely demanding. For instance, the RADA model, which was released just a month ago on February 18th, can understand the entire context of a sentence simultaneously. When generating from the beginning sequentially, the coherence with the content at the end isn't quite right. However, the diffusion model generates everything at once, so it gradually aligns with the overall context. While the transformer model infers the next part by understanding everything it has read so far, the diffusion model looks at the entire context simultaneously. Initially, the approach involves randomly masking certain words, starting from this masked state. Then, you can understand that the gaps are gradually filled through a process of diffusion. This paper is divided into 3 sections, all of which involve masking. Each section is independently masked, resulting in specific parts being left blank. Simultaneously, the mask predictor component is responsible for estimating the missing parts based on the overall context of the text. This is a part of the pre-training phase, where a large corpus of text data is utilized to probabilistically mask certain words. After masking, the process involves randomly predicting the masked words to complete the text. The first stage involves pre-training, where the model learns what should ideally be included in the context. The second stage is supervised fine-tuning, where specific prompts are input, and if the responses are paired correctly, the model undergoes additional training to generate accurate outputs. Think of it as a version with binding applied. Finally, the third phase involves actual inference, where sampling takes place. When everything is masked, you need to progressively unmask it, so you can envision it as progressively moving down with a mask plate, reapplying the mask, and then gradually reducing the masking again to generate the final output. Unlike traditional transformers which predict the next part in a sequence, this model introduces random gaps throughout the sequence, enabling a comprehensive understanding of the entire context. Think of it as a process of iteratively filling in the masked sections. This approach is detailed in several research papers. So, what exactly does this entail? Looking at models like GPT 4.5 or QN 2.5, they excel in forward predictions. They score 82.7 and 75.9 respectively. However, they struggle significantly with reverse predictions. However, this model called LATTER, which uses the diffusion model, is generally quite similar. Of course, overall performance is still low, but this is something that needs to be improved over time. As the model grows larger, it could potentially improve further. From the perspective of the entire model, the red part represents LATTER. When viewed at 8 billion parameters, it is well balanced overall. When comparing Llama 2 and Llama 3, we see that they both provide solid performance and are quite competitive. Moreover, as the model scales up and the number of flops increases, the calculations scale accordingly. This adheres to the scaling law, and while we are currently discussing smaller models, we can progressively shift towards larger ones. Unlike a startup like Inception, if major tech companies take this initiative and heavily invest in GPUs, they can progressively develop better models. Hence, from the GPU standpoint, this can be seen as a traditional ARM model. To evaluate a transformer model, you need to sequentially generate QKV, perform matrix multiplications, apply scaling, masking, and softmax, and then repeat the matrix multiplications. Moreover, for multi-head attention, you have to input V, K, and Q separately. On the other hand, with a model like Radia, you can generate the entire context in a single step. Without the need to constantly reprocess and refine the input iteratively, you can handle long text in a much more streamlined and efficient manner. By filling in the missing parts along the way, it seems to greatly enhance the efficiency, allowing for the processing of a larger number of tokens. Since it can perform parallel processing, it's expected to significantly reduce computational latency with GPU-friendly parallel processing operations. Moreover, if applied to edge devices, the lightweight technique allows for efficient sampling, enabling the creation of a model capable of real-time operation. The first commercialized model of this kind is called Mercury. Given that it has been released, I made a quick summary. Since it's a startup, the server infrastructure isn't fully developed, which limits scalability. Instead of utilizing expensive GPUs like Cerebras with vast amounts of SRAM, they opted to fundamentally alter the algorithm. By modifying the AI model, they managed to achieve this rapid performance. This is very significant, so please share your thoughts. Moving forward, the diffusion model, as advocated by Yann LeCun, a scientist at Meta. Yann LeCun often says transformers aren't the answer. This view is spreading. GPT 4.5 is out, but its performance isn't improving much. That's why diffusion models are getting attention as an alternative. It seems to have come out at the right time. I'll keep you updated.